So far we have learned how to implement all the four control sources using the MOS transistor. We also discussed how to implement the voltage control voltage source and the current control voltage source using an op-amp. Okay, all these circuits are based on negative feedback, and sometimes there is a great deal of confusion when talking about negative feedback and a related concept which is known as virtual short. What we'll do in this lesson is to discuss this business of virtual short and how it needs negative feedback with a very large gain in the loop. Okay. Now let me first take the op-amp examples which are easier to discuss, and specifically I'll consider the voltage control voltage source using the op-amp. You also know that this is what is known as the non-inverting amplifier. Okay. We have an input signal Vi and we have a voltage divider from the output. Okay, and this is Vd, and let's say the gain of the op-amp is A0. That means that the op-amp is equivalent to a voltage controlled voltage source of gain A0. Okay, this is V0 and this is Vd. Okay, now we have already analyzed and found that V0 by Vi equals K by 1 plus K by A0, or V0 equals Vi times this number. Okay, and the difference voltage Vd is V0 by A0, which can also be written as Vi, the input voltage, times K by A0 divided by 1 plus K by A0. Okay, now what happens as A0 goes to infinity? This number of course becomes equal to K as A0 tends to infinity, and this Vd tends to 0 as A0 tends to infinity. Okay, so that means that the voltage difference between these two terminals will tend to 0 as A0 tends to infinity. If A0 is infinity, these two will be at the same voltage, and this is what is known as the virtual short. Okay, now if you have some 2 points, let's say 2 nodes, and then you short circuit them with a wire, then clearly the voltage at this node and this node will have to be exactly equal to each other. Okay, they may have been different before you connected the wire, before you shorted them, but after you short them with the wire, the voltages have to be the same. Now in this circuit, we have a situation where the voltage at this node and this node will have to be the same. Okay, if A0 is infinity, and they are not shorted by a wire. Okay, so they are not really shorted to each other, they are not connected at all. In fact, if you use this model, it looks like there is an open circuit between them. But the negative feedback action with a very large A0, that is an infinitely large A0, makes these two voltages equal to each other. So then in such a case, we say that these two nodes are virtually shorted. Clearly they are not really shorted, there is no wire connecting them, so these two nodes are virtually shorted. Okay, and this is true for any op-amp circuit which is operating in negative feedback, and the op-amp's gain goes to, and when the op-amp's gain goes to infinity. Okay, we can also take the current controlled voltage source example. we know that the output voltage is II times Rm divided by 1 plus 1 by A naught, and this difference voltage Vd of the op amp is, in this case, V naught by A naught, which is II Rm by A naught 1 plus 1 by A naught. Okay. So again, this Vd tends to 0 as A naught goes to infinity. That is, the input terminals of the op amp are virtually shorted. Again, this happens because A naught equals infinity. Okay. Now in this particular case, because the positive terminal of the op amp is connected to ground, when they become virtually shorted because of gain becoming infinity, this node here also is at 0 volts. So sometimes it's also called a virtual ground. That is, its voltage is guaranteed to be at 0 volts, but it's not shorted to ground through a wire. Okay, so that is the virtual ground. Many times there is a great deal of confusion about why this virtual short comes about. Okay, it's not that if you just take an op amp and do nothing with it, there will be a virtual short between its terminals. You have to configure the circuit in negative feedback, and the gain of the op amp has to be very large. Of course, if you buy an op amp, its gain will be very large. Okay, because the op amp circuits are useful only when the gain of the op amp is very large, and the designers of the op amp do take care to make sure that the gain is very large. But it's up to you to put the op amp in negative feedback. Then these two terminals will be virtually shorted, and lots of very useful functions can be realized with this property. Okay, and also this virtual short business makes it very easy to analyze ideal op amp circuits. And even when the op amp is real, that is, the gain is not quite infinity, you can still go ahead and assume virtual shorts and analyze the circuit. What you get will be the approximate transfer function or approximate gain of the op amp circuits. Okay, so many times you just look at an op amp circuit and you can tell what it is doing. After that, you can put in the finite gain of the op amp and analyze the exact transfer function. Okay. So sometimes there is some confusion about why the virtual short comes about, like I just mentioned, and there is some confusion about whether it comes because the input resistance of the op amp is infinite or 0 or something of the sort. Okay, it's very easy to see that the resistance of the op amp, that is, let's say that there was some internal resistance between the two input terminals of the op amp. It's very easy to see that it plays absolutely no role as far as the virtual short is concerned. Okay, in fact, for that it's easy to first consider an op amp in which there is no resistance and we have A naught tending to infinity. And if the gain becomes infinite, we know that this is at 0 volts and these two are virtually shorted. Okay, and it's because of the finite gain. Now you can connect whatever resistance you want between this. Okay, so that corresponds to a resistance that may be there inside the op amp. I am drawing it outside, but it may be inside the op amp. What is the voltage across this resistance? It's 0 volts. So it carries no current. So it makes no difference to the Kirchhoff's current law equation here. So it makes no difference whatsoever to the circuit. Okay, so if the gain is infinite, the input resistance of the op amp makes absolutely no difference, and the virtual short is not because of the input resistance, it's because of the gain being infinite. Okay, and similarly the same goes for the output resistance. The output could have some series resistance. Okay, and you can do a similar analysis and find that it has absolutely no effect whatsoever. Okay. Now another way to think about this virtual short business in an op amp is that because the gain is infinite, okay, and the output is finite, that is something we have to assume, and the output will be finite only if there is negative feedback. If it is positive feedback, it could be diverging off to infinity. Okay, if the output is finite, then the input, which is output divided by the gain, has to be equal to 0. So the input voltage is 0 for any finite value of output. Okay, and similarly here, for any finite value of output, the input has to be 0. The thing that has to be guaranteed is that the output will not diverge off to infinity, and that's guaranteed by negative feedback. If you do have positive feedback, you will find that the steady state output will go to infinity. Okay. So this is what virtual short is all about. It also happens in circuits using a transistor as long as there is negative feedback around the transistor. Okay.